Hello, this is Jeff Hamrick at the University of San Francisco's MSFA program, and I'm going to talk for a few minutes about multicollinearity diagnostics in Stata. So imagine this is the body fat percentage data set we've worked with on several occasions as a kind of basic example this semester. Suppose that I regress body fat percentage against age, weight in pounds, height in inches, and neck circumference, chest circumference, and abdominal circumference. So a priori, there's no reason why we can't get an OLS fit out of this regression relationship. There doesn't appear to be anything wrong from the regression output, but because some of these independent variables like weight and height and neck and chest and abdominal circumference are likely to be positively correlated with one another, and probably very positively correlated with one another in the case of, for example, weight and abdominal circumference, we suspect that this model may in fact have a multicollinearity problem. So recall with me that multicollinearity by itself does not bias the fitted coefficients in a regression model, but that it generally speaking biases the standard errors of those fitted coefficients upwards. It inflates the size of the confidence intervals that we build for those coefficients upwards in terms of their length, and therefore it tends to bias student t-test statistics downwards as well, and it creates a problematic situation in terms of evaluating a regression model. The most extreme case of a multicollinearity problem is when you don't end up with significant t coefficients right here, but you do end up with a significant overall regression relationship. Now, we don't have that in this case since, for example, abdomen and weight are both highly significant, but that's kind of the most extreme example of multicollinearity that you can find. So the most common way that we assess whether or not we have a multicollinearity problem is by computing the variance inflation factors, which I discussed in some detail in class. So let me go ahead and recompute those again. You'll recall that the variance inflation factor tells us the extent to which the standard error of the coefficient of interest, these guys right here, has that the variance, that is the square of the standard error, has been inflated upwards. So a rule of thumb is that we do not want the standard error, that is the square root of variance, to have been inflated more than twice its basic size, its most minimal size under a minimal model. So that means we're worried about variance inflation factors that are equal to 4 or greater. So there are only 3 here that appear to have that problem: weight, abdomen, and chest. And there's no exact rule as to how we should proceed. We could probably remove weight from the model, and then all of these variance inflation factors will change again, and maybe we will then view them as being non-problematic. So, for example, if I now regress body fat percentage against all of the variables ignoring weight, and then I recompute variance inflation factors, what we see is that we still kind of have a problem. There's still probably a problem with abdomen and chest, but for example, the VIF associated with neck fell a little bit, though it wasn't much of a problem to begin with. So what we might do is continue to explore this process of dropping variables from the regression relationship. Like maybe I will only put in abdomen and I will not put in chest. So we'll do these 4 right here, and then I generate the VIFs, and now I've got a collection of variance inflation factors that are all underneath 4. That means that the standard errors are not being inflated by a factor of 2 or more. In fact, roughly speaking, the standard errors are being inflated by the square root of these VIFs, which is not all that big. So by removing weight and chest circumference, we appear to have corrected the multicollinearity problem in this model. Okay? There's another way, going back to the first regression relationship that we were considering, the one that had all of the variables in it. There's another way to kind of get a sense as to the multicollinearity problem and the influence that it's having over your model. That is to actually have Stata report for us the estimated variance covariance matrix of the fitted coefficients. Okay, so this is not the variance covariance matrix of the raw age, weight, height, etc., data, but rather the variance-covariance matrix of the estimates of the coefficients in the regression model involving those variables. And because you can call that up by simply using the command VCE. The problem, of course, with the variance-covariance model is that it is not scale-free. It is not invariant with respect to changes of location and scale. So we'd rather work with a correlation matrix instead of a variance-covariance matrix. And so the way we do that is we put the core option after VCE, and now we're looking at a correlation matrix instead. That's a little bit easier for us to understand. So what we see, for example, is that weight and age are, the coefficients for those are surprisingly positively correlated, whereas neck and weight are surprisingly negatively correlated. If we look further, we see that abdomen and weight are negatively correlated as well. Now let's be careful once again about what we're saying here. Abdomen and weight are, of course, the raw data, positively correlated. If a man has more fat around his abdomen, he's probably going to weigh more in pounds. This is the correlation matrix for the fitted coefficients in the regression model, and the relationships between the correlations here tend to be the opposite of the relationships of the correlations of the raw data. So what do I mean by that sentence? I mean that if abdomen and weight, for example, are positively correlated, the raw data, the fitted coefficients in a regression model will be more likely to basically have a negative correlation, okay? And so here we would be concerned for negative correlations, or particularly positive correlation, as is the case with age and weight, let's say of magnitude 0.5 or higher. So this one strikes us as being a problem, and this one right here strikes us as being a potential problem as well. Now this doesn't tell us what to remove, since you could always remove, for example, either age or weight to get rid of one of the variables that's creating this positive correlation, this particularly positive correlation in the correlation matrix of coefficients from the regression fit. It doesn't tell us which ones to remove, but oftentimes if you remove one of the offending variables, then the remaining variable tends to be less offending with some of the other variables that are left in the model. Okay, so these are two diagnostics tools in Stata that we can use to assess multicollinearity. These don't provide fixes. The fix that I've prescribed for you is to drop variables from the model. Other fixes include collecting lots and lots of additional data, which can tighten up the width of our confidence intervals and reinflate some of our test statistics that have been deflated by the overestimated, the biased upward standard errors caused by multicollinearity. There's another technique too called ridge regression, which we will not learn in this class. It's not usually viewed as being particularly effective by most economists. So let me know if you have any questions. Good luck with your homework.